Hello everyone, my name is Caitao Zhan from Stony Brook University. Today my topic is efficient localization of multiple intruders in shared spectrum systems. Table of contents. Introduction. The radio frequency spectrum is a limited natural resource in great demand. Therefore, the US proposed the shared spectrum paradigm to increase utilization. Nowadays, software-defined radio technology gives ordinary people easy access to RF spectrum, both receive and transmit. There comes a security threat. Selfish users can transmit data on shared spectrum without authorization. So our problem is to find out the selfish, unauthorized users. This defines our problem, the title, efficient localization of multiple intruders in shared spectrum systems. The shared spectrum is when the primary users and secondary users share the spectrum. The primary users are licensed, and they are always authorized to transmit. The secondary users are unlicensed, but when they are given permission, they are authorized to transmit. However, there are transmitters that are unlicensed and not given permission, and they still transmit. We call it an intruder. The intruders will interfere with the authorized transmission. Our goal here is to localize them. This is an illustration. We have some authorized primaries and secondaries. We distribute a crowdsourced sensors. The sensors are to monitor the spectrum. At some point, some intruders come out, and they will interfere with the authorized ones. So we need to localize them and estimate their power. This is the problem definition and challenges. Consider a geographic area. Assume a single channel. We distribute a set of crowdsourced sensors that report received signal strength identifier. There are three types of transmitters: the primaries, the secondaries, and the intruders. We define a problem called MTL-SS. It is given the observations from the sensors, localize the intruders, and estimate the intruders' power. The challenges are threefold. First, the sensor receives only a sum of the signals from the multiple intruders transmitting simultaneously. Second, there are multiple targets to localize, and some of them might be close to each other. And third, there are a dynamically changing set of authorized users in the background. For this talk, we largely assume no background users, no primary and no secondary users, and there is only intruders and sensors. So we focus on the multiple intruder localization problem. In the higher level, our approach is MAP, or maximum a posterior. First, we define a hypothesis. A hypothesis is a configuration of intruders, or a set of location power pairs. On the right-hand side, it is a picture of a single hypothesis. This single hypothesis represents two intruders with two different locations and two different power levels. Maximum a posterior, or MAP, is machine learning. In the machine learning pipeline, there's a training and testing. For the training, we need to collect the training data. The training data here is the probability distributions of RSSI at sensor locations for each hypothesis. This is how MAP works. Given the actual sensor observations of RSSI, compute the following Bayes formulas and pick the most likely hypothesis. There are some pros and cons of MAP, maximum a posterior. For the pros, it provides the optimal classification accuracy. There's no need to assume a propagation model and allows to estimate the intruder's power. And fourth, it can be extended to solve the MTL-SS problem with background users. There are some cons also. First, it has high computation cost. And second, there's high training cost. First, we mitigate the high computation cost by a divide and conquer technique. And second, we mitigate the training cost by first, interpolation, and second, only train for a single intruder. assuming conditional independence, and utilizing the power summations. In the following sections, I will focus on how we mitigate the cons. First, I will introduce the map star. It optimizes the map. The core idea of localizing multiple intruders is a divide and conquer technique. First of all, the faraway isolated intruders can be localized independently. And second, the close by intruders in a cluster are localized later. So there comes two procedures. In procedure 1, it localizes the isolated intruders. Here, a hypothesis represents a single intruder. We run map at appropriate local areas. At procedure 2, it localizes the multiple intruders situated close by. Here, a hypothesis represents 2 or 3 intruders. The key here is we construct the multiple intruder probability distributions from training data of the single intruders. Then we run map at appropriate areas. Here is an illustration of map. So here we see 4 red intruders and a bunch of crowdsourced green sensors. The 4 intruders, there are two intruders that are isolated, and there are 2 intruders situated close by. For the procedure 1, it can successfully localize the isolated intruders. However, it cannot deal with the intruders situated close by. And here's where the procedure 2 comes from. Procedure 2 is designed to localize the multiple intruders situated close by. With procedure 1 and procedure 2, all the intruders can be localized. Now let's talk about the training. We reduce the training via interpolation. The idea here is to construct some probability distributions and estimate others via interpolation. During the training phase, we deploy the sum sensors at a coarse granularity. We do the training and collect the data, and then we interpolate the other finer granularity locations. So the key here is how we interpolate. We introduce a novel interpolation technique, ILDW. The key idea of ILDW, or inverse log distance weighting, is two. First, we take advantage of the known transmitter location during the training phase. And second, we modify the inverse distance weighting. It assigns weights based on the distance in the logarithm domain. So first, let's take a look at the traditional IDW. Here we have a red transmitter, 2 blue receivers, R1 and R2, and we want to interpolate the unknown R0. Here we observe that the R0 is at the center of R1 and R2. When during the IDW, R1 and R2 will be given 2 equal weights. However, in ILDW, in the logarithm domain, R0 is not at the center of R1 and R2 anymore. We see that R0 is closer to R2 compared to R1. So since R2 is closer to R0, we think that R2 should be given a higher weight. So we designed a new equation that bring up the weights. We see that in IDW, R1, R2 weights are equal. And in ILDW, the weight of R2 is larger than R1. So with this computation in the logarithm domain, we see that ILDW will give a lower interpolation error. And here is some extensions with the background users and power estimation. MapStar can be extended to incorporate some changing set of background secondary users via online training. And then we derive a closed form formula solution to estimate the power of intruders in the continuous domain using the maximum likelihood estimation. In this talk, I will not elaborate on these 2 points. Here are the evaluations. First is the MapStar. We are comparing to a clustering-based solution and also Splot. This figure is the localization performance of various algorithms in a large-scale simulation. for varying number of intruders. We can conclude that map star has a lower localization error and sum of miss rate and false alarm rate. This is the evaluation for minimizing the training cost. This figure is the localization performance of map star in a large scale area for varying training data. We can conclude that with around 10% of real training data and 90% of interpolated data, MapStar can give a good localization performance. We also did a test bed for MapStar, both indoor and outdoors. Here I'm going only to present the indoor one. On the left side, the figure is the software-defined radio devices we are using. And on the right side is the figures, photos of the indoor lab environment. Here are the results. From the plot, it is the localization performance of various algorithms in an indoor testbed for varying number of intruders. We can conclude that MapStar has a lower localization error and a sum of miss rate and false alarm rate. Now we draw the conclusions. We developed an efficient learning-based method for the multiple intruder localization problem in shared spectrum. We also introduced interpolation method, ILDW, and power estimation method. Thank you for listening. Is there any questions?
Great, thank you for an excellent talk. Let's see if our participants have any questions. The audience, please either use the raise hand feature or you could also send in your questions by the chat window. And maybe while we wait for that, I had just kind of maybe a comment. So, one way I could see your work with respect to prior work is kind of extending from the single unknown node to multiple intruders in your case.
Yes.
So there are prior works on Bayesian localization, and one in particular that shows that if you have a particular objective function with respect to localization error, you can measure localization error in terms of mean squared error, you can measure it in terms of minimum absolute deviation, you can measure it in terms of likelihood that the error is more than some distance, etc. And so there's actually some literature showing how you can take the a posteriori probabilities and then apply any arbitrary cost function and optimize based on that. So instead of just picking the maximum a posteriori probability locations, you can pick the location that would optimize whatever metric you care about. So it's a way to kind of maybe generalize your work to also other metrics beyond or in other dimensions beyond just picking a maximum point. But I think the methodology that you presented here would more or less carry through probably even for these other extensions. So I just wanted to mention that to you. I can maybe offline share with you some of the papers that have done that.
Okay, that would be great.
So trying to see if we have any questions from the audience.
I have a question if nobody else does.
Please go ahead, Neil.
So I wanted to ask about the computational complexity. What techniques have you come up with to keep the computational complexity low? Just judging the number of hypotheses would go up exponentially with the number of cells, I guess, the discretization of your space. And I'm wondering how. Maybe you can talk for a second about technique to minimize.
That is a great question. So when we are conducting the maximum a posterior, we are only doing it in a local area. So there's a stuff called the transmission radius. Mm-hmm. At each location, we only consider the sensors that are inside a transmission radius. So the map is operated in a small local area.
Okay. And do you limit the number of cells that can have, or limit the number of transmitters in some way?
Yeah. So in procedure 2, we are localizing multiple intruders at the same time. in the implementation, we limit the number of intruders to 3.